Good evening, everyone. Yeah, we're good. Hi, I am Leslie Crone. I have the privilege and honor to lead the communications team here at Argonne National Laboratory, and we are really excited to present this out loud lecture tonight for you on quantum. There will be fun, there will be science, and I'm giving away a secret. There are prizes, and I got to tell you, these are really rare things. I've never even seen them myself. I've worked here for 5 years, so they are rare things. So we hope that you will participate. I am here to give you a couple of housekeeping notes, and the first one is for our online audience. So they have dialed in via a platform we call Vimeo, and when they come into that platform, we turn their cameras and their microphones off. That is normal. You sometimes have trouble hearing on Vimeo, so there's a button that unmutes the audio feed. You want to do that. And if it's not loud enough, there's also a volume bar. You can slide that volume up and down. So a few tips for our remote participants. If you are interested in closed captioning, there's a button that turns that on the lower right-hand side of your screen so you can read. I will tell you, AI is good, but it's not great, and it really is it stumbles over some scientific terms, so bear with it if you're watching the closed captioning. Tonight, we are doing something we haven't done with an Out Loud before, and we are going to use some technology that we call Poll Everywhere. It's a way for everybody in the audience, both in the room and at home, to interact with us, answer some questions, play a few games. So if you want to grab your phone, you can do this right now. They will say this again later in case you need a refresher. But you want to text a message to the phone number 22333. So the phone number is 22333. And in the subject or in the body copy, you want to type in all one word, Argonne Events, ARGONNE-EVENTS, all one word, Argonne Events, to that number 22333. Hit send. You'll get a message back that says you've joined the event. And hang on to that. You'll be able to answer some questions later on. Again, they'll give you a refresher if you need that later in the event. If you're having any trouble online, folks, please send an email to our outloud@anl.gov email address, and they'll help you troubleshoot. By participating in the event, we are recording this. It'll be available for folks on YouTube after the event, but by participating, you're consenting to being recorded, so we thank you for that. And now I get to introduce our laboratory director. So Dr. Paul Kearns has been leading the laboratory since 2017. And we're delighted to have you here to kick us off.
Thank you very much, Leslie. It is fantastic to see the people here in the auditorium as well as those joining online. Welcome, everyone, to our very first Argonne Out Loud lecture of 2023. I am Paul Kearns. I have the real honor of serving as the director of Argonne National Laboratory. Very special place, and we'll share a little bit of our science and what we do, and you'll get a chance to meet a few of our researchers this evening. So really fantastic opportunity to engage with the community, so we're pleased you're participating. It's a pleasure to provide this program both in person and virtually. This hybrid format certainly allows us to share our cutting-edge research and pivotal discoveries with a wide audience, so we're very pleased to do that. Since Argonne's beginnings in 1946, we have unlocked new science frontiers. We are keeping our nation at the forefront of the transformative technologies of tomorrow. That's what the laboratory is all about. This is especially the case for quantum innovations. We are achieving dramatic advances in computing, communications, and sensing. These technologies have the great potential to revolutionize national and financial security, patient privacy, drug discovery, and the design and manufacturing of new materials. They will also increase our scientific understanding of the universe and further open scientific disciplines in ways we have yet to imagine. I can't think of a more futuristic field than quantum technology, and lately, Hollywood seems to agree. A recent film on the quantum realm was Ant-Man and the Wasp, Quantumania. Given the popularity of the Marvel franchise, I'm assuming that many of you have seen this action-packed motion picture film that is inspired by scientific innovation. I thoroughly enjoyed the movie too, but it's difficult for many of us to distinguish between the factual and the fanciful. And this is especially challenging for a highly complex topic of quantum technologies. That's why we are presenting this two-part dive into the quantum universe. First, you'll hear from two scientists who are leading cutting-edge research on quantum communications. Carol Scarlett is here this evening. She's the founder of Axion Technologies, which is part of the innovation program we have here at the laboratory called Chain Reaction Innovations. That's Argonne's embedded entrepreneurship program. Her startup is developing the next generation of encryption devices, a true random number generator. And then Martin Holt is here this evening as well. He is a group leader of the Electron and X-ray Microscopy group at Argonne Center for Nanoscale Materials. He is leading trailblazing research on predictive controls of local structure physics in quantum and classical materials. I'm sure you got all that. Like you, I look forward to hearing about their research and perspectives on today's advancements. In the second part of this program, you, our audience, will also have the opportunity to test your quantum knowledge. Together, we'll learn what's true and what isn't. That's what's technical jargon and what's technical sounding gibberish. Don't worry, you won't need a PhD in quantum computing or particle physics to win. You just need an inquisitive mind, which you've already really confirmed by attending tonight's visit and participating. Moderating tonight's lecture will be Jillian King-Cardwell and Andres Salas, both from our communications and public affairs team here at the laboratory. Jillian and Andre work with two areas of the laboratory that are currently undergoing remarkable renewal. Jillian supports the Argonne Leadership Computing Facility, which is installing the Aurora supercomputer. Just behind us here in this facility, this exascale machine will come online later this year, becoming one of the fastest computers in the world. I'd like to think it's going to be the world's fastest at the time, but we'll see if that's true when it indeed happens. Over 2 exaflop in terms of operations per second. We're quite excited by that. And Andre assists the Advanced Photon Source, which will provide even more powerful high-energy X-ray beams after its current upgrades. The upgraded APS will be 500 times brighter in terms of the X-rays it delivers for our scientific experiments at the laboratory once it's commissioned. Physical construction starts here next month on the upgraded APS. Before I hand things over to them, let me briefly tell you about the transformation of Argonne, which is well underway this year. Together, the new APS and ALCF, as we refer to them, will transform how we do science, not just here at Argonne, but across the broader scientific community. These are national scientific user facilities, so researchers from academia, from industry, from around the world, honestly, can come and use these facilities, so we're quite excited about that. Combined, they will empower our researchers to make discoveries at unprecedented speeds. No other laboratory has a comparable dynamic duo like this, each boosting the power of the other. These upgraded user facilities will be key to us accelerating the quantum technologies that drive U.S. prosperity and security. We are honored to deliver these innovations for the country right here at Argonne and in the Chicago region. Since we're celebrating cinema and science tonight, it might be easier to show you more about the transformation of Argonne with a movie trailer.
In a world where the needs of humanity are charging forward, where the big questions need bold answers, where our greatest frontiers of exploration might be hidden in our own minds, it's time for a new generation of tools to illuminate our future. Find out what happens when America's brightest light source meets the world's fastest supercomputer. A new era of science is dawning. New opportunities for collaboration will arise. Breakthroughs will emerge faster than ever before. Researchers are calling it a game changer for the future of energy storage, material science, and global security, and hailing it as a revelation for research into human health, clean energy, and climate resilience. APS and Aurora, discovery at the speed of light. Only at Argonne.
Well, there you go. You got to have a little fun, and they are truly transformational in terms of the capability they'll bring to the laboratory and the science we do. So let me say thank you, everyone, for attending our Out Loud lecture. I'll now invite Jillian and Andre to start tonight's program. Please join me in welcoming our host.
Good evening.
All right. Thank you so much for being here, everyone. We're excited to have everyone in here and out there and everywhere you're watching the show. I'm your host, Jillian King Cargyle. I am an Argonne communicator, a professional science appreciator, and an expert on the Marvel Cinematic Universe. This evening, we're going to take you on a journey into the quantum realm. It's a great place to be, and we've got some fun and games that we are going to have tonight in the quantum realm. Soon, I'm going to introduce our scientists who will help us separate the science fact from the science fiction. But first, please welcome to the stage my co-host, my Andy Richter, Andre Salz.
Hello, everyone. Thank you again for being here. My name is Andre. I, like Jillian, am a science communicator, a Marvel enthusiast, and tonight I'm the official scorekeeper. So for those of you lucky enough to be contestants, now you know who to bribe. I take
That's
cash,
right.
check, Vimeo.
Get those bribes in quick, because tonight we're going to talk about quantum principles, but hopefully in a way that everyone can understand. As communicators, we love our metaphors. And one of the most famous metaphors is Schrodinger's cat. You may have heard about this. Physicist Erwin Schrödinger came up with the hypothetical cat to illustrate the quantum principle that we'll talk about later in the evening. And this thought experiment, the cat, which is fittingly in a box, because we know that cats love boxes.
They sure do, Jillian.
This cat is both alive and dead at the same time. According to quantum physics, it remains in that fuzzy, ambiguous state until we observe it. And then it is definitively alive or dead. But again, not until we observe it.
That's fascinating, Jillian, and thankfully completely hypothetical.
Yes, very hypothetical. Andre, don't you have a cat?
Yes, I do.
What's your cat's name?
Oh, it's Penny Lane.
Oh, that's so cute. Does she love boxes?
Yes.
Well, we're in for a treat because tonight Penny is going to help us illustrate Schrodinger's cat throughout the evening.
What?
That's right. We're going to check in on Andre's cat, Penny. Will she be alive or dead?
I do not like this game, Jillian.
I know. Tonight she will be both alive and dead at the same time until we observe her. Let's have a peek now. Let's switch to that cat cam.
Penny.
Oh, it looks like she's alive this time. Way to go, Penny. We'll come back to Penny later in the program and explain the real-life principle that she is part of. Doesn't that sound like so much fun, Andre?
Oh, so much fun, Jillian.
I thought you would like it. So, on to our program. Tonight we'll be talking about real-life quantum science and about the way that science is portrayed in superhero films. Specifically, we'll be talking about Ant-Man and the Wasp: Quantumania, the most recent film in the Marvel Cinematic Universe. For those who haven't seen them, the Ant-Man films are about a family of scientists and one lovable criminal who use technology to shrink between the atoms. In the films, the heroes find themselves in something called the quantum realm, an entire universe that exists on a tiny, tiny scale. So tonight we're exploring our own quantum realm to separate the factual from the fantastic. Let's bring our scientists to the stage now. Please welcome Carol Scarlett and Martin Holtz.
Thank you.
All right, Carol and Martin, thank you so much for being our guides as we make our way into the quantum realm tonight. We're going to start by having you tell us a little bit about yourselves and your research. So, Carol?
Oh, hi, everyone. I'm Carol Scarlett. I am a PhD in experimental nuclear physics And I am also the founder of a small tech company, Axion Technologies LLC, where I use the quantum property of photon polarization to produce photonic random walking to extract randomness for use in encryption and other data devices.
All right. And Martin?
Hi, I'm Martin Holt. So I work at the Center for Nanoscale Materials right here at Argonne, and also at QNext, which is the Quantum Research Center. And we were actually trying to answer these fundamental questions about how to create quantum systems in the real world and how to integrate them into physical devices. And to do that, we actually use incredibly powerful X-ray microscopes that harness the power of the advanced photon source, which is a synchrotron source of X-rays, produces laser-like X-ray beams. And this lets us look inside quantum materials and see how the bonds of atoms are flexing right near these atomic scale quantum systems. And then also see the response. So if you can match up the structure around these quantum objects with how they're responding, then you get the rules to the game of how these quantum systems behave in the real world. So it's March Madness, right? Imagine that if you're attempting to figure out the rules of basketball just by watching the game, right? Sounds off. You don't want to admit to anybody you know nothing about basketball, right? You are just watching the game, watching the players play the game. How long would it take you to write down the rules of basketball? How many games? Or what kind of camera angles would you need? Would you need to zoom in to see if it's a foul or not? Wow, that wasn't a foul at the beginning of the game. That's only a foul at the end of the game, right? Something like that, that it only comes up every so often. You need a lot of observations to do. So that's the flavor of what we do, both in quantum material systems and also material systems. Argonne is learning by observation, both using these powerful imaging techniques and also computationally by simulating them in the supercomputers that's behind the wall over there. And that lets us kind of harness the power of these things for real technologies by understanding the real world rules of that game.
All right. Very cool. We're going to start by talking about the science that inspired Ant-Man. So I have some questions for you, and we'll see if you can help us separate the fact from the fiction. So, first off, is the quantum realm a real thing? If so, what is it like, and why do we study it? Carol?
Quantum mechanics is definitely, of course, a real thing, and quantum interactions is a real thing. So the quantum realm, yes, there's on a very infinitesimal scale, on the atomic scale and below, materials behave differently than the way they behave in our everyday life. So in everyday life, we experience what we call classical effects. These are the well-understood phenomena. You push something, it moves in the direction that you push it. On a quantum scale, when we go to interact with the material can somehow behave in ways that we had not anticipated. And we're going to get into more of what that is. Martin does a lot of research in this area, so I'm going to let him follow up.
Yeah, well, I mean, the question of the quantum realm is from a scientific perspective. How close do you have to look before the behavior of the material that you're looking at represents the actual quantum nature? I mean, if you look around you, all the properties of the materials that you see are in some sense defined by quantum principles. But if you need to see individual quantum states or the underpinnings of that, you need to look, as Carol said, look quite closely. Has somebody played Minecraft? Yes, I knew those folks would. Yeah, there's some huge models there that look very realistic, and the question is, how close do you have to be before you can see the blocks, right? Before you can see those fundamental units that are built up and how they're put together to create these huge, fantastic effects. And it could be models of ships or planets or anything like that, but it's answering things on that length scale and time scale that is, in some sense, the quantum realm.
All right. So Ant-Man's quantum realm imagines a world full of different life forms. Could anything really be alive in the quantum realm?
This is going to be one of those, with what we know today.
Yes.
I mean, the behavior of quantum materials and quantum properties is weird and strange, right?
Yeah.
But it is in some sense predictably weird. We have incredibly powerful mathematical tools and scientific tools to observe and create repeatably this quantum phenomenon, even if it's kind of statistical or probabilistic. So, is an atom alive? Pass. Phone a friend, right? But, this sort of behavior isn't demonstrating anything that would be unexpected or that would potentially create new theories, I would say.
I would agree with him. I would add to that and say that when we think of miniaturizing things or things being on a very small scale, and you ask yourself, okay, could you have similar sort of behaviors and particles and universes? And with what we know today, of course, we have this really, really, really big universe that's on the extreme opposite of quantum scale, and yet there are quantum effects that show up all the time. So could you rescale that to something smaller? Not with the physics we know right now, but I'm always hopeful that there's something I don't know and that we're going to learn, and that's why Argonne has this amazing computer to simulate. So maybe. I'm going to give it a maybe.
I like maybe, and I like predictably weird. Andre, that should be our new band name.
Absolutely.
All right, excellent. So I'm going to list some things from the movie's Rapid Fire, and we're going to see if it's possible or impossible. Okay? Shrink rays.
Not yet.
Not yet. Okay. Grow rays.
Not yet.
Not yet. Shrinking and growing the space between the atoms.
Right? We could cool them down or heat them up, but not in that way.
Not in that way. All right. Quantum entanglement to communicate across great distances.
Yes.
Okay. Quantum entanglement between Paul Rudd and Michelle Pfeiffer.
It's Hollywood.
Well, if their distance scale is small compared to the velocity of light and for 5 seconds, then yeah, basically.
Yeah, basically. All right. I'll take that. All right. Quantum phasing to walk through walls. Uh-oh. Talk it out.
Okay.
Keep trying.
We're trying. We're trying.
Yeah, the concept of tunneling will work, but I don't recommend trying at home attempting to tunnel through a wall.
No.
That's the safety first, I feel.
So, yes, the concept of tunneling we see all the time in nuclear physics. We don't understand the itty-bitty details, so if it's a genuine walking through walls, we do have theories of other types of particles. All of you have probably heard of dark matter particles. That's what my company's named after, by the way, Axion. But they're dark matter particles that we believe can allow things to walk through walls. So I'm going to give it a thumbs up, even though I understand why he gives it a thumbs down.
All right. I'll accept a maybe.
Scientific process.
Yes. All right. So what is the real power of quantum? We've talked a lot about Ant-Man, but how will quantum technology appear in our everyday lives in the near future?
Well, I mean, we've already harnessed some of the statistical powers of quantum things for many, many years. I mean, the concept of a laser was a demonstration experiment in the 70s. It was rooms full of equipment, and now it's been miniaturized down to, something you can have on your keychain, right? An atomic clock, the GPS. A lot of these things evolve and become into everyday technology very rapidly. But the concept of actually addressing individual quantum states and trying to encode information in them and use it as the information process is relatively new, and that's in its infancy. But it allows us to do entirely new types of computing, sensing, and communication that potentially can't be done, even in principle, by their classical counterparts. And that gives us the edge for entirely new classes of technology. So not just faster, but very, very different. And that's, I think, the promise of the harnessing quantum effects on a real device scale.
And I would echo what he says, that quantum will empower things in our everyday lives, because as we can compute faster, we can make better decisions. We have artificial intelligence that will benefit from all the computing power and the promise of quantum computing, and being able to make decisions very quickly. This will improve medicine, this will improve communications, and this will improve fun. You'll be able to access movies faster maybe one day. So.
All right. And speaking of movies, we're at a national lab celebrating a movie called Ant-Man. And that's a little weird, right? But how do you see science and fiction influencing each other or playing off each other? And how does that play out in quantum science?
Well, I think one of the things that happens when we see science fiction, there's always someone out there, some young person like some of the children that are here in the audience who's thinking, I wonder if that could really work. And that sparks whole new areas of research. So I was saying to Martin earlier that I remember 20, 30 years ago, if you told someone, hey, we're going to do nuclear fusion with lasers, oh, they would have just cracked up laughing. And they probably would have hauled you off in a straitjacket. But today we actually do. Because even though lasers have 1/1,000,000th the energy of most nuclear interactions, when you put enough energy into a system, you can drive effects. But that's because people thought about it, wanted to do it, tested it out, wanted to prove the principle, and so they went out and researched it. I think having people fueled up on is this really possible? Can this really be done? Is what generates the next topics of research. And that's what generates advancements for everyone.
100% agree. It's the power of the human imagination that's fed by science fiction. I am a true believer in science fiction. I'll say that right there. And it's no coincidence that in the 40s and 50s, most of the science fiction was dominated by rocket ships traveling to other planets, like Martian Chronicles, 1950, Ray Bradbury, right? And so in the 60s, when there was a national call to put a person on the moon and return them safely to Earth, there was a whole generation of scientists and engineers that say, yeah, we got this. With this slide rule, we got this. Okay. I mean, how courageous was that? There's a few folks that are nodding here because it's the optimism and courage to push the boundaries of what we know to be true today because you've seen it. You've seen it in science fiction, and you can work towards something that might not be here in the real world today. I'll end rant there, but that's the basic idea.
All right. Well, thank you. Thank you for those answers. And now we're going to check back in on Penny. Alive or dead? Oh.
Get out of the box, Penny.
Come on. She can't. Andre.
Oh.
But she was alive, so that's good. All right. Now we're going to move on to the next phase, jargon or gibberish. And for that, I am going to need a volunteer from the audience. All right, you, sir, come on up. Why don't you come up the ramp? We love safety here at Argonne. You could come up the ramp for safety. I'll meet you there. All right, welcome. Thank you for being brave. And this game is called Jargon or Gibberish. So, and what was your name?
I'm not on television, am I?
You're streamed. You're in everywhere.
I'm used to gibberish, but my name is Dan.
Okay, Dan. Andre, tell him what he signed up for.
Welcome, Dan. Here is how to play jargon or gibberish. You will be presented with two scientific terms, one of which is completely made up. So your job is to guess which one is real, the jargon. You score a point for each correct answer. There are 3 questions in the quiz. If you win 2 points, you win the game.
All right. Any questions?
I'm good.
All right, Dan. And now, as we said before, audience, you can play along. And if you want to play from your seats, you can get out your number 2 cell phones and text Argonne Events, all one word, to 22333. And we'll give you a few seconds to send a text and join poll everywhere. Andre, are you participating in the poll?
No, Jillian, I'm reporting a catnapping.
Oh, they'll never make it in time. Okay, so is everyone ready? Let's get started, Dan. Okay, first up, quantum supermomentum, the phenomenon describing how a physical system can travel at greater momenta than allowed by the speed of light. That could be real. Or quantum superposition, the phenomenon describing how a physical system can exist in multiple modes at once. We're going to give you a little bit of time to think about it. Well, our folks at home and in the audience are thinking about it. They might give you a hint. Who knows? Let's see how they're doing. Oh, there's some voting happening. What are you thinking, Dan? You think you have an answer?
To pick which one is fact
Which one do you think is real?
or that's
All right, turn around. You got some help from the audience here. Quantum supermomentum or a quantum superposition?
It was super momentum. Final answer.
Supermomentum. What do we think, Andre? Oh, Dan. That's all right. That's all right. Let's move on to, do you want to explain?
Yeah, so the quantum superposition, which is the real thing, is actually what allows us to. Oh, thanks. So quantum superposition is actually what allows us to do what all the complicated things we'd like to do with these individual quantum states. Because these states can, either be in, one state or another state. If there's a probability of it being in either, then it is actually in either someone all the time. And that lets us create a state that's a mixture of multiple states. And so a quantum bit then can encode very dense pieces of information. It's not just 50-50, like the poor cat in the video, right? But it can be 70-30, 40-60. So if you imagine you're trying to encode like a baking recipe into a quantum bit, and you have some ratio of eggs to flour that you would like to bake with. It can go all the way from, 50-50, which you're going to get kind of a pound cake, right? Or 70-30, you're going to get out like pasta, 10-90, you're going to get like a quiche or cheesecake or something like that. But all that continuum of stuff can be encoded into a single bit, a single quantum bit. And so that'll just kind of give you a flavor of the density of information that you can pack into one of these objects, and then we can start stringing them together.
And I would add to that, of course, the Schrodinger cat in the box experiment, which says that there is a good chance that the cat is still doing very well. But I would also say that this is the idea that that things in the classical world exist in a particular state. I'm sitting in a particular place. But in the quantum world, there's this fuzziness where if you specify a particular place, then you lose access to other bits of information. So things exist in a superposition of states. So I'm here, but perhaps I'm also standing on the other side of the doorway.
All right, you have all that?
I believe Star Trek's warp speed is super momentum, and that subspace does exist to create super momentum. So I think you don't know what you're talking about.
Oh, we're in the Marvel universe though tonight, so different fandom. It's okay. All right, so we're gonna quiz you again though. All right, here's the second one. Quantum stoppering, a phenomenon in which a quantum object can close an energy gap between two quantum objects, allowing them to glide toward each other and meet in the middle. Could be. Or quantum tunneling, a phenomenon in which a quantum object passes through a barrier that it does not have enough energy to surmount. All right. Our friends in the audience and at home are going to help us out here and vote again as well. What do you think? Quantum tunneling, oh, looks like we've got some people on quick draw here. What do you think? You want to look at the board or just go rogue? All right.
I think I've heard of quantum tunneling, so that's where I'm going.
All right, we say quantum tunneling. Okay, quantum tunneling. Yes, you were paying attention. I think we covered that one, so we'll move on to the next term. Okay. Quantum entanglement, a special relationship between two or more particles in which they are inseparably correlated no matter how much distance separates them. Or quantum entitlement, a characteristic exhibited by a particle after it absorbs the energy and position of another nearby particle. What do you say? What do you say out there? What do you say out there? Let's help our contestant out. Uh-oh.
Can I phone a friend? Wait, entanglement.
Entanglement? Is it the answer, Andre? Heyo! All right. All right. We'll have Carolyn Martin, would you like to say anything about quantum entanglement?
Sure. So quantum entanglement, as explained, is where you have a system of particles that have interacted with one another and they form some quantum state. So that as they separate, there's still information about the original quantum state. So if I collapse the one over here and this particle turns out to be spin up, then I already know that this one has to be spin down if the two were together a spin zero system. And this is something that we see all the time in various quantum effects. Martin can tell you more about what happens with laser lights and with polarization and other effects.
Yeah, well, I mean, this is really where the fun begins, I think, for quantum information sciences, because you've prepared these states, you've created these systems, you've protected them from everything. Now you get to play Lego, right? You get to put them together and make relationships between the pieces of information that didn't exist before. And these can be very complicated relationships. These things can determine on each other. And let's get to a class of computing, because all of these bits know what the other bits are doing all the time. And they cooperatively decide on, sort of what is going on based on these fixed relationships that you put in between them. So it's not a linear chain of computation like in a classical computer. And so entanglement is, the relationship between information. You can see that in your daily life. If you prepare 2 lunches, one for you, one for your partner, brown paper bags, you grab one, you walk out the door, and, around lunchtime, when you open that bag, you'll know whether or not you got the wrong lunch, right? And not only that, you'll know instantly what somebody else is eating half a city away and whether you need to apologize to them. Okay.
And I'll add one more point to that. This is such a unique effect. It's even goes beyond just sort of the classical phenomena where I know I had a red ball and a blue ball and they both went into a brown bag. This goes to beyond the speed of light. When you collapse the system over here, this system over here knows where it was supposed to be. So this gets into very spooky action at a distance, I would say.
All right. Well, let's see how our contestant did, Andre.
Jillian, Dan only got 2 points, but since everything in the quantum realm is small, that is enough to win the game. Congratulations.
Oh, well, you can return down the ramp, and Alex will be meeting you to give you your prizes, because everyone is a winner, unless they're a loser, but we won't know until we observe you. So, all right. We need another volunteer from the audience. All right, this person must be bold and unembarrassable and have stamina. You have it, sir? Okay, he says. Well, join me. Come on up that ramp. All right. You are our next volunteer. And what is your name, sir?
Hayden Johns.
Hayden, okay, come over here. You need a special spot in the middle of the stage right there. And we are going to play our next game, and that's called Let's Get Entangled. All right. I can tell you're excited about it. So, Andre, why don't you tell our contestant how it's played?
Certainly, Jillian, and welcome, Hayden. You may be familiar with the copycat game, sometimes called the mirror game. Your job in Let's Get Entangled is to copy whatever Jillian does here on stage. If Jillian makes a sudden movement, you make that same movement. No matter what Jillian is doing, you keep copying her movements. Your goal is to convince the audience that you and Jillian are entangled and that no distance or interference can keep you from mimicking her movements. And since particles are entangled for life, you'll need to do this forever. Or at least through the next game.
All right. That's a big commitment. What do you think? Okay. All right. Okay. We're ready. Are you ready? Okay. Did you start? We're starting right now. We started. This is it. Okay. You're in. Back, up, down. Okay. We got our squats in. Good. All right. Now we, as you are up here being entangled with me, we're going to have a few lightning rounds of another game we like to call Headline or Head Game. And I'm going to need 2 more volunteers to come on up. You, ma'am, come on up. You, sir. All right. Please take the ramp for safety. All right. So we'll have one of you play at a time, and you can just wait. Excellent. Safely on the ramp. Huh? Oh? Okay. All right. Okay, and what's your name?
Aaron.
Okay, Aaron, you're going to play Headline or Head Game, and Andre is going to tell you how it's done.
Hi, Aaron. Jillian will read a quantum science headline. Your job is to determine whether it's real or made up. If you think it's real, you say headline. If you think it's made up, you say head game. This is a lightning round, so please answer at the speed of light.
Sound good?
Yes.
Okay. All right, let's get started. Black holes could reveal their quantum superposition states. New calculations reveal. What do you think? Headline or head game?
Head game.
Answer? Oh, okay. Let's try another one. Scientists pit solid state and superconducting qubits against each other. Factions ensue. Headline or head game?
Head game.
Hey, all right. Okay, here's another one. Maximum quantum computer power calculated to be the equivalent of 10 human brains. Headline or head game?
Headline.
Answer? Oh, okay. Stability in asymmetry. Scientists extend qubit lifetimes.
Headline.
What do we think? All right. All right. So that was the end of round 1. And why don't you tell Andre, tell our contestant. Oh, wait, there is one more. Oh, there's another one. Ant-Man must have snuck it in. All right, are we ready? Researchers set record by preserving quantum states for more than 5 seconds. Headline or head game?
Headline.
That's correct. All right. Let's tell him how he did.
Congratulations, you got 3 out of 5 correct.
All right, that's fantastic. So, slightly slower than the speed of light, but we have Alex coming to give you fabulous prizes. So you can make your way down the ramp, and you did fantastic. So good, I want to dance a little bit, just a little bit, and spin around. Okay. So, Carolyn Martin, let's talk about that 5 seconds.
So yeah, I mean this is a super cool result. I'm very excited by it, just because the lifetime, or how long a quantum state has until it loses its fidelity, loses its information, decays away, is one of the fundamental challenges that almost all ways that we have of creating these quantum systems run into. And this was a very special type of communication to the qubit that allowed to change a quantum state into then a charged state, which was much easier to read out, and was able to get them to, in a very perfect system, about 5 seconds. And these lifetimes are typically, just not in the human realm of being long. And so imagine, you're distributing rapidly melting ice cream cones to your family, right? And they're arguing about who gets what flavor, right? You only have a certain amount of time for that argument before everybody just has a cone. Okay, these things are melting quickly, right? So the amount of computation you can do scales with the amount of time that it can stay relevant and maintain its information. If you had to reboot your computer every 5 seconds, you wouldn't necessarily be too happy about it, but this is the breaks when it comes to quantum computation. It also lets communication get one step closer to reality, because you can send quantum information anywhere in the globe over fiber optic channels or up to satellites and back. And over 5 seconds, you'll have enough time to get it back and compare it to the original state. Say, hey, did you get that? Is that okay, right? And that sort of thing wasn't really able to be done before. So this is a huge step forward, I think.
So when you asked me whether or not Michelle Pfeiffer could talk to, I forget the other actress name. Well, when something is moving at the speed of light, if you send this information out optically, the speed of light is 186,280 miles per second. That means the moon is roughly 250,000 miles. in under 3 seconds, the signal could go to the moon and back. And so even though 5 seconds sounds like that would be a pain to keep restarting your computer, 5 seconds for a photon is a really long time. That's a lot of distance. And so this is what makes it a really exciting results because, okay, fine, it's not on the human scale much time at all, but it's on a scale where, yes, they would be able to communicate in this quantum realm.
Excellent. All right. And that result was from right here at Argonne and the University of Chicago. So we like to brag about that. It makes me want to dance. I'm so excited for no reason. All right. And you've been waiting patiently. Why don't you come on up? And we are going to play another round of headline or head game. Are you ready?
Yes.
And what's your name?
Maria.
All right, Maria, we're going to jump right into it. Physicists create the smallest, crummiest wormhole you can imagine. Headline or head game?
Head game.
Tricky there. I can imagine some pretty crummy wormholes, but we'll get to that later. New techniques use quantum sensors to measure magnetic fields at the atomic scale. What do you think?
Headline.
Answer? All right. Scientists propose renaming the field of quantum computing Quamputing.
Head game.
Andre, what do we say? Very good. It should be true. Scientists take note. It's a good name. All right. Researchers demonstrate quantum entanglement in particles separated by a galaxy.
Headline.
Okay. Chicago scientists are testing an unhackable quantum internet in their basement closet.
Head game.
Andre, what do you say? That one is actually real. All right. And how many points did our contestant get?
She got 2 out of 5 correct. Thankfully, it's not a competition, Jen.
All right. But that's not bad, and that's prize-worthy. So, Alex, we'll meet you with your prize. Thank you so much. Oh, I just love just running my hands through my hair. What do we think? Has he been entangled long enough? Yeah, all right. Congratulations. We'll disentangle you a little bit early. And we'll have Alex meet you. So, Carolyn Martin, that last headline was from the Washington Post about a quantum network that is being built right here in Chicagoland. Can you tell us about that?
Yeah, I mean, this is, again, a partnership between the University of Chicago and Argonne to develop a real-world system for testing quantum communication. And this is a 50-mile loop that goes from University of Chicago to, and it is a very small closet in that basement that those poor grad students have to work at. And it terminates in the building actually across the parking lot here, and then also continues up towards Fermilab for a bit. And this is, again, speaks to that idea of learning by observation, that you don't know the problems that you might run into in establishing a real-world quantum network without actually trying it. So what sort of noise do you have from these interconnects? What kind of dissipation or attenuation of the photons do you have? Is there a day-night cycle? Trucks driving over it? Like real-world effects and communicating this quantum information. And this type of quantum communication is super cool. And I think Carol's been working a lot with that, but you can give 2 quantum states to different people to enable completely secure communication. So imagine you have like 2 twins that don't like the same food. Okay, whatever one kid likes, the other kid doesn't like. They like asparagus, doesn't like asparagus. This one likes pizza, doesn't like pizza. If you separate out these twins and send them to different houses with the same menu, okay, both these houses are going to have a very identical list of what these kids like and what they don't like. It's just going to be flipped around, right? And they can use that list to communicate to each other as the basis for a code. And because even if you see the menu, you haven't had dinner with these children, okay? You don't know the answers to these questions. And so the basis of these codes, or the keys of these codes, can be exchanged through quantum information to create the secure communication. Sorry, this is a terrible example for a very elegant field of mathematics that I encourage you to look into. But I don't know, Carol, you got another.
Well, I'll add on to what he's saying. So I once worked for Southern Bell, which is a phone company. And Southern Bell was converting from the old copper lines to the new fiber optic lines. But the biggest concern about converting to fiber optic lines is that you have photons running along this little optical pipe. And if you bend it ever so slightly, you'll drop the signal by a tiny amount, which is imperceivable. But some hacker in the middle can pick up your conversation. So you could bend it by a tiny amount and put a little device, and then you could have what's called a man-in-the-middle attack, where somebody gets to know all the information. If you're trying to send your bank your code so that you can log in, somebody can sit here with a little device and get to see all of that. Can't do that with quantum states. Once you entangle those quantum states, so he gave an eloquent example of the two kids, I'll give maybe a little slightly simple example. So let's say I have a system where I have red balls and blue balls, and I have mixed them together. And so then I just say, okay, I'm going to send one out, I'm going to send one to this guy. But I don't know that he's trying to hack me. He's trying to listen in on that conversation. With regular fiber optics, that's possible. But with an entangled system, when he tries to listen in, he collapses the state. So I immediately know, hey, something has happened. The state has collapsed. I called this guy up, and he's got something that's noisy. He's like, look, this system is purple. I don't really know what it is. I don't know whether it should have been red or blue. I now know that there was an attack in the middle, and I now know somebody else got the keys. So this is the type of problems we can solve, communication problems, real world problems, because this can really happen. Fiber optics, you can go look it up. You bend it just a tiny bit and you lose enough of the signal that somebody can sit and listen. Can't sit and listen on a quantum entangled system. That's the beauty and the security of this type of system, which is why, as he says, rightly so, it is worthwhile to invest. In fact, the University of Chicago has invested in a quantum accelerator program, which I participated in, along with Chain Reactions Innovation here at Argonne. My business participated in the duality program. So Chicago is a hub for building up quantum information and building the support staff and educating people and building the hardware, testing the hardware. So those of you who live in this area, you're in the right place.
All right. Fantastic. So when it comes to quantum, Chicago really is the place to be. We have our own quantum realm right here. That's exciting. And it's almost as exciting as seeing whether cats are alive or dead. So let's check in on Penny one more time. Oh, look at that, Andre. She made it through.
Jillian, this was not my favorite game.
I know.
But I'm happy to see that Penny has all of her 9 lives intact.
Me too. I'm pleased about that. And now we have some time to have you here in the live audience and you at home get your questions answered by our experts. So, live audience, if you have any questions, you can come to the mic in the middle of the room. And online audience, to submit your questions, you can find the chat window to the right of your screen, enter your name, and submit your questions. So, anyone who'd like to ask a question, come on up to the mic in the middle.
Hello. I don't know when they'll be available commercially, but part of the beauty of that technology, so classical computing involves ones and zeros. You have systems that sit in well-defined deterministic states. Quantum computing takes advantage of this entanglement, what we've been talking about. It takes advantage of the fact that this system, I can now have qubits that interact with one another and that know what the other one is. So I don't have just a 1 or a 0 and just a 1 or a 0. I have a 1 or a 0, 1 or a 0, and these guys communicate. So I literally have a third state, which means in terms of information, if you know binary system, for every bit that I have, it can be 1 or 0, so it has 2 states. So you can go 2, 4, a 16 and you can start to build out how much information you can store. Well, you can store more information with quantum qubits because of this whole property. But I'll let Martin tell us when they're going to come out.
No, I mean, honestly, there are quantum computers out now these days that you can apply for, time and log on to. IBM has them online that you can see the results coming out, and it's already very fantastic because it's a more general type of computing than a classical computer. So by creating the relationships between these qubits, you can actually have it mimic real-world things. Like if you have it mimic chemistry, it can predict entirely new types of chemical activity or materials. If you have it mimic gravitation with the types of interactions that we know are involved with gravitation. That was the 9 qubits that demonstrated that wormhole in the headline that you saw earlier, right? Or if you try to have it do optimization problems, it can do incredibly fast optimization problems that even the most powerful classical computers, I'm sorry, Paul, they're the ones coming online soon, which are fantastic, but they can't necessarily access it. These problems aren't just scientific curiosities, like how to manage a national power grid and make real-time decisions, how to manage logistics over the entire planet. These types of questions can't be addressed, even in principle, by the most powerful classical computers we can make. But these types of optimization problems are some classes of problems that quantum computers can do much, much better. So that will give us the tools we need to meet these complicated challenges that we're facing.
I have one from our online audience. How soon will there be a quantum internet?
Well, I mean, if you're saying just communicating between here and Chicago, we've got that one down, right? But we have to solve some fundamental problems about how to cope with these losses of information. So what types of qubits you need to make refresh stops to make sure this quantum information stays current, what kind of modulation or communication protocols make the best advantage of it. But, when people were building the original internet, they kind of declared victory once computers had their own names and could send files to each other, for scientific research. And at the birth of that, people weren't thinking about, YouTube or TikTok or things like that. So we are on the cusp, and that is one of the goals of QNext, which is the Quantum Research Center here at Argonne, is to actually create real-world quantum interconnects to make the quantum networking become a reality.
Hi, my name's Josh. We'd opened the talk discussing observing quantum systems to understand the rules, but we've also spoken since and said that observing quantum systems changes the system itself. So how far are we from a research point of view of understanding what scale systems are governed by quantum mechanics and otherwise classical mechanics, right? Do we know what that scale is? Do we have a specific number, or where are we with that?
Yeah, I mean, that is a number that is relatively straightforward to calculate. Like you can say, hey, at this point, you're going to really see normal statistical mechanics, and at this point, you're really going to see quantum statistics take over. The difficulty is really creating it. Like, how do you make it a reality? How do you bring it into the world as an actualized system, right? And then use it for a technology. So some of these concepts of like where it changes over are extremely well understood. Like why quantum behavior is the way it is, and why so those are much larger questions. But right now we're at the point of attempting to use it for new technologies. So we're quite a bit there, I would say, in my perspective.
I would offer up that definitely at the atomic scale, which is which is at the angstrom scale, about 10 to the minus 10 meters. Definitely at that scale, you are dominated by quantum mechanical properties. That is, most of any type of measurement you would try to make at that scale, you're going to see the quantum fuzziness. You're going to see entanglement. You're going to see these effects that we've been talking about. The fact is there's kind of a continuum as you go up because, obviously that's the way things work. Things are fundamentally at those scales built out of atoms. And so as you go up to a macroscopic scale, as you sort of grow to even just very thin film, you start to lose some of those quantum properties. But now there's still quantum effects that we see on a large scale because we produce lasers. So we produce are able to take materials and pump energy into them and have all the energy come out in this nice coherent photonic state. So there are some overlaps even at the large scale where we see the results of quantum effects. But certainly by the time you're down to a few atoms, you are down in just real world terms of like what scale this is about a meter, how far do you need to go. At the, I think maybe nanometers, tens of angstrom scale, you're dominated by your quantum effects. You're welcome.
Another from our online audience. Is it really possible to use quantum entanglement for faster than light communication, or is that still subject to relativistic laws?
So it's a bit complicated to describe. You could use the states as a vehicle to have information that potentially is related to each other in speeds that are faster than light. Are you able to communicate that to the other person that has it? Well, no, you still sort of have to text them and be like, oh, hey, you need to do this to this quantum state. And then you'll see this, right? And so that's sort of the no communication theorem, that there's two parts to the process. You give a quantum state to somebody else and you tell them what to do with it. And the telling them what to do with it part is the part that's still I'd recommend looking it up. There's a lot of stuff that goes here in order to understand it.
All right. I know that there's people who still have questions, and if you're here, I encourage you to stay and ask your questions, but we'll wrap it up for the main audience and for the folks at home. If you still have questions at home, you can email them to outloud@anl.gov, and we will have our experts get to your questions. So just by being here tonight, all of you were winners. Don't you agree, Andre?
Absolutely, Jillian.
All right. Thank you. And let me thank again our awesome scientists, Martin Holt and Carol Scarlett, for taking us on a journey and for all of the fun and illuminating answers that you've given us tonight. Thank you to our AV crew and to the organizing committee for making this event possible. Thanks to Marvel and Disney for giving us so many awesome science-based entertainment things to riff off of. And thanks once again to our wonderful audience for making tonight a treat, and all of you who came up on stage and were so brave. That was awesome. And I do need to note for safety purposes that no cats were catnapped. It was all in good fun, wasn't it, Andre?
So much fun, Jillian.
And if you want to learn more about Argonne and all of our science, register for our open house, which is coming up on May 20th. We're so excited to let you know all of the amazing things that are happening here. So thank you so much and have a wonderful night.